Students, welcome to the second session of our third module in compressible fluid flow. So students, this third module is dealing with normal shock waves. So in the first session of this particular module, we have already discussed what actually is normal shock is meant by and what are the different types of shock waves, like stationary wave, like moving wave, and like weak wave and strong waves. And another classification is like a normal shock wave and oblique shock wave. So such types of such types of normal shocks in compressible fluid flow we have studied in the first session. And we have also discussed the assumptions or the general characteristics of normal shock waves, such as like perpendicular. The shock waves are perpendicular to streamline, right? And the second one is shock. This shock wave has the shock wave are very thin in nature, very thin in nature, and they take place at a constant area. Third one, it is frictionless, okay, frictionless, so we can neglect shear forces and all. And fourth one, adiabatic, so there is no heat transfer. So uh, while taking the energy equation, we can neglect that q heat transfer. And fifth one is like no external work. And sixth one is body force is negligible. Body force is negligible. So these are the characteristics or the assumptions that are being used while deriving the equations for normal shock wave. Okay. So students, now we will discuss the governing equations for this particular shock, normal shock. So what are the governing equations? So already we have studied four types of governing equations, right? Four types of equations. What are they? First one, conservation of mass or continuity equation. Second one, momentum equation, conservation of momentum. Third one, energy, conservation of energy. And fourth one, entropy equation. Entropy equation is based on the second law of thermodynamics. Okay. So these are the main or the very inherent governing equations that should be used while analyzing these type of situations. Okay. So students, now I will go before analyzing these equations, I will draw an image or a figure representing normal shock wave. So students, let there be a flow through a constant area duct. Uh, Suppose this represents a normal shock, a compression wavefront. So flow is happening. Suddenly a shock wave is produced. So this is normal shock wave. So you can see that the direction or the geometry of that shock wave is like it is perpendicular to the direction of the streamline. So let this flow rate be m dot, and after that shock wave also the flow rate remains same. Okay. Now I am taking a control volume across this, a small control volume across this shock wave. So I will enlarge it and draw another page. Okay. So let this be a shock wave. Okay, this is a shock wave. So it is perpendicular to the direction of the flow of streamline. Suppose this is the boundary of that duct. Okay, and I'm taking an infinitesimal control volume. Okay, control volume like this. Let the let the length of this control volume be dx. Okay. Suppose this section be 1 and the next section be so this is the section in upstream and this is section in the downstream of the flow. Suppose this velocity here be m1, Mach number be velocity in the upstream be v1 and Mach number be m1, pressure be p1, temperature be T1 and stagnation pressure corresponding to this particular section be P01. Similarly here V2, M2, P2, T2 and P02. Okay. So this is the control volume. Okay. So this is the control volume. So students, this is a stationary normal shock wave. Okay, this is a stationary normal shock wave. Normally taking place in what kind of stream? Supersonic stream. So mainly normal shock always takes place in a supersonic stream. Okay, so this particular figure shows the control volume, illustrating the kind of stationary normal shock wave. So the control volume considered here is of infinitesimal length. It encloses the stationary shock wave. So the length of the control volume is infinitesimal enough to accommodate this particular, or the infinitesimal enough to accommodate the thickness of this shock wave. Actually, the thickness of shock wave is of the range of 10 raised to minus 7 mm. So the shock wave will be this much thin. Okay, very thin. So we have already we have already discussed that general characteristic of a normal shock. This shock wave are very thin. Okay, very thin. So usually their order is of 10 raised to minus 7 mm. Okay, so the control volume considering here is in its length. The length of the control volume considering here is having an infinitesimal length which is just enough to accommodate this particular thickness of what? Normal shock wave. Okay. And there will be an abrupt change. What is the peculiarity or the function of what actually is happening while a shock wave occurs? There will be an abrupt change in flow parameters, right? Mainly pressure gets increased abruptly and velocity and Mach number get reduced. So there will be a change in flow parameters. That is why I have mentioned a particular set of flow parameters in the upstream and a particular set of flow parameter in downstream. Okay. Now we will move to the governing equation. So first one is mass equation, right? Continuity equation. So students, you know that continuity equation is nothing but m dot equal to constant. M dot means mass flow rate. Mass flow rate is rho 1 A1 V1 equal to rho 2 A2 V2. So students, since we have considered a control volume, we have considered the normal shock wave as a thin shock wave was very thin. It can be considered to take place at a constant area. Okay, so thin area means we can consider A equal to constant. Okay, A equal to constant. So you can see that this particular area in the upstream and this particular area in the downstream are I will show with the reading. So this area, this cross-sectional area and this area is considered as same only. So constant area. So area is constant. A1 is equal to A2 equal to A. So suppose this is nothing but m dot, right? So m dot by A is nothing but rho 1 V1 equal to rho 2 V2. Okay, why? Because A1 is equal to A2 equal to A. So that is based on the general characteristics of normal shock wave. So what is m dot by A? M dot by A can be written as G or mass flux. Mass flux. mass flow rate per unit area, that is mass flux. So mass flux is constant, or rho1 v1 is equal to rho2 v2, right? Okay. Now what is the second governing equation? Conservation of momentum. Conservation of momentum. Momentum equation. So actually we are considering here one-dimensional steady flow. One-dimensional steady flow. Okay. We are studying only one-dimensional steady flow in this whole course. Whole course of this particular subject. All of every flow we are studying is one-dimensional and steady only. Okay. So for one-dimensional steady flow, we can write conservation moment equation. Summation of force will be equal to. Actually, it should have been like dou by dot t of m dot v. Okay, over the control volume plus m dot v out minus m dot v in. This should have been the actual conservation of momentum equation if it was general flow, that is unsteady flow. Since this is a steady flow, we can cancel this dou by dot t. Any term which has got dou by dot t as the differential, it can be considered as 0 because it is steady flow. So no parameter change with respect to time. Every parameter which depends upon time will be taken as 0 if the flow is considered to be steady. So sigma f equal to m dot v out minus m dot v in. That is the equation of one-dimensional steady frictionless flow. So actually here no friction also. So what is the sigma f term here? It is nothing but sum of the forces acting on the control volume. What is sigma f? Sigma f is sum of forces acting on the CV control volume. So what are the forces acting on the control volume? Here actually pressure P1 is acting in this side and pressure P2 is acting on the downstream. So P1A1 will form a force and P2A2 will form another force, right? So I will write sigma f is nothing but P1A1 minus P2A2. Okay, they both are acting in opposite direction. That is why one is positive and another one is negative. Why? So you know that. So if P1A1 is acting like this, P2A2 will be acting in this opposite direction. They will try to compress that particular control volume, that particular straw. So that is sigma f. So actually the equation is like sigma f is equal to m dot v out minus m dot v in. So I can write P1A1 minus P2A2 is nothing but m dot v out means m dot is constant itself. So you don't need to use any suffix or prefix in subscript for m dot. You just use a suffix for v. So v2 minus m dot v1. So this is the conservation of momentum equation. So you can write P1A1 minus P2A2 as, so since m dot is nothing but rho AV. So m dot here I am writing as rho 2A2 V2 into a V2 is there minus rho 1 A1 V1 into this V1 is remaining. Okay, and you can simplify it as P1 A1 minus P2 A2 as rho 2 A2 V2 square minus rho 1 A1 V1 square, but A1 is equal to A2 is equal to A, right? Constant area. So you can be written as P1 minus P2 is equal to rho 2 v2 square minus rho 1 v1 square, right? So students, you have to note a particular point here. I am writing this equation like this since we have discussed, or we have studied, or we have understood the fact that there are no while studying the discussing the general characteristic, there is no friction means there is no shear force, there is no body force. So in this equation you don't have to take the or in while taking the sum of forces, you don't have to add that body force and shear force in this particular term. Only pressure force is required. Only pressure force is acting in that particular control volume. There is no body force, there is no shear force, because in the general characteristics we have already told, in case of normal shock, body force can be neglected, and the flow can be considered as frictionless, so there won't be any shear force. So this is the equation for conservation of momentum. Let me rearrange it like this. I am taking this rho 1 v1 square to left hand side and p2 to right hand side. So it will become v1 rho 1 v1 square equal to p2 plus rho 2 v2 square. Okay. So this is one equation. This is the equation for conservation of momentum, and this will be the equation of continuity equation or conservation of mass equation. And we have got one more equation to write, so that is nothing but energy equation. So third is energy equation, conservation of energy equation. So since this is a steady one-dimensional steady flow, and the elevations are taken, z1 is equal to z2, and q is equal to 0, right? Adiabatic, since the process is adiabatic, q is equal to 0, and also we have told that w is equal to 0, there is no external work. So applying all these assumptions, we can write the energy equations as nothing but h1 plus v1 square by 2 is equal to h2 plus v2 square by 2 is equal to h0, is equal to a constant. H0 means stagnation. The value of stagnation enthalpy, that is enthalpy when the velocity is 0. So that is h0. Okay. So this is the third equation that might be required while deriving the conditions of the equation for the normal shock. So ensure that all these three equations are okay for you. So these equations are simplified based on the general characteristics of the normal shock wave. Students, now we will move to the equations for normal shock wave. So very important, this equation is known as Prandtl Meyer equation. Prandtl Meyer equation. So very important. The derivation for this particular equation will be asked in the university exam. So there are high chances of asking this particular equation in university exam. So be very sure. So I am writing all the three. Given equation here once more. Rho 1 v1 equal to rho 2 v2 equal to m dot a equal to g. Okay, equal to constant. Again p1 plus v1 square by 2 is equal to p2 plus v2 square by 2 is equal to what? It will be F by A, okay, force by area. Don't worry, you don't need to write that. It will make you confusing. It will be constant, and again h plus v1 square by 2 is equal to h2 plus v2 square by 2 equal to h0 is equal to a constant again. So these three are the main equations that will be required to solve the or the obtain the expression for the condition for normal shock. So students, I'm taking this particular equation. Okay, I'm writing that equation again. P1 plus momentum equation, P1 plus sorry, I have written this equation wrongly. Kindly excuse me. So it should have been rho 1 v1 square, right? Rho 1 v1 square plus rho 2 v2 square, right? So what was the equation we have derived? P1 plus rho 1 v1 square equal to P2 plus rho 2 v2 square. So P1 plus rho 1 v1 square plus P2. Okay, I will write it once more. P1 plus rho 1 v1 square plus P2 plus rho 2 v2 square. So I am writing this equation once more. P1 plus rho 1 v1 square equal to P2 plus rho 2 v2 square. Okay. Now I am rearranging this equation by taking rho 1 v1 to denominator plus v1 is equal to P2 by rho 2 v2 plus v2. So I am dividing the equation, the whole equation with rho 1 v1. Rho 1 v1 is constant, right? Rho 1 v1 is equal to rho 2 v2 equal to constant. So I can divide it in both LHS and RHS. So this equation can be written as, what is actually done? I am dividing with rho 1 v1 here. I am dividing with the same rho 1 v1 here, but rho 1 v1 is equal to rho 2 v2. So I am dividing it with the rho 2 v2. So we will get an equation like this. Okay. So students, my aim is to reduce or simply or change this equation, or my aim is to eliminate all this pressure density terms here and just keep velocity and acoustic velocity terms only. So I have to change or transform this equation such that the only terms here are the velocity or acoustic velocity. The flow velocity or acoustic velocity terms should be remaining in this particular equation. All other terms, pressure and temperature or density terms should be eliminated. So that should be our aim. So in order to eliminate P1, actually P1 by rho 1. Actually P1 by rho 1 or P2 by rho 2 can be written as P1 by rho 1 equal to, for perfect gas, P1 can be written as rho 1 RT1, right? So P1 by rho 1 can be written as RT1, right? Similarly, P2 by rho 2 can be written as RT2, right? So I am substituting these two equations here. P1 instead of P1 by rho 1 and P2 by rho 2, I can write it as RT1 and RT2 respectively, right? So I am writing it as RT1 by V1 minus RT2 by V2 is equal to V2 minus V1. Okay, since I've taken this V2 to I've taken this V1 to LHS. Okay, sorry, V1 to RHS. So RT1 by V1 minus RT2 by V2 is equal to V2 minus V1. Now since you have got RT1 here, so if you multiply a gamma with this particular equation, you can get gamma RT1. So gamma RT1 can be written as acoustic velocity square, right? So I am multiplying with gamma here. So in RHS also. So what is gamma RT1? Gamma RT1 is A1 square, right? A1 square by V1 minus A2 square by V2 is equal to gamma into V2 minus V1. So students, very interesting. We have eliminated pressure, temperature and all other terms. density terms, and now only A1, A2 and V2, V1 remains. Okay. So students, now I have to eliminate A1 and A2 also and bring A0 into the picture. So what should be done? So you know that what is enthalpy equation? Enthalpy is nothing but Cp into T, right? Cp can be written as gamma by gamma minus 1 into R, and T remains. So gamma RT is nothing but A square, right? A square by gamma minus 1, right? So we have already studied the adiabatic energy equation. Adiabatic energy equation like A square by, so so the energy equation is H plus V square by 2, right, equal to constant, right? So instead of H we can write A square by gamma minus 1 plus V square by 2 is equal to H0. So this constant can be H0. So H0 can be written as A0 square by gamma minus 1, right? So this equation we have studied in first module, adiabatic energy equation, right? So based on this equation we have drawn an ellipse, right? So hope you remember that portion. So A square by gamma minus 1 plus V square by 2 is nothing but A0 square by gamma minus 1, right? So A square from this equation you can write A square as A0 square minus gamma minus 1 by 2 V square. So I am rearranging this equation to get A square, a particular expression for A square. So A square can be written as like this. So A1 square is nothing but A0 square minus gamma minus 1 by 2 V1 square. And similarly A2 square is nothing but A0 square minus gamma minus 1 by 2 into V2 square. Right? So students, I am substituting for A1 square and A2 square. Okay. So A1 and A2 will be eliminated and A0 V1, A0 V2. So the equation will become in terms of A0 and V1, A0 V1 and V2. Substituting A0 square minus gamma minus 1 by 2 V1 square by V1 minus A0 square minus gamma minus 1 by 2 V2 square by V2 will be gamma into V2 minus V1. So where have I substituted this? I have substituted this that expression for A1 square and A2 square in this particular equation. Okay, don't confuse. I am substituting A1 square and A2 square in this particular equation. So we will obtain this equation. Okay. Now I am rearranging this equation. So rearranging means so just do one thing. You bring all the terms. So you bring this term to LHS. So A0 square, and I am dividing individually with V1. So I am dividing A0 square by V1 and gamma minus 1 by 2 V1 square by V1. So it will yield gamma minus 1 by 2 V1 square and V1 cancel. So V1 remains. Similarly minus A0 square by 2 plus, so since it is inside the bracket, while bracket is opened, it will be, this particular sign will become positive. So positive gamma minus 1 by 2 V2, and I am bringing that gamma V2 minus V1 to the left side. So it will become minus gamma V2 minus V1 is equal to 0. Okay. So I am taking A0 square as common. So A0 square is taken as common for this. So actually it was V2. Okay. V2. Don't get confused. Maybe I will be writing. If I am writing any wrong term, you should be vigilant enough to note that particular mistake or fault I am committing here. Okay, hope you are following me tightly. So that should be the important aspect or the characteristics that a student should own. So I'm writing it as A0 square 1 by V1 minus 1 by V2. So I have taken A0 square from these two terms as common. Okay. So and what is remaining? So these two terms are remaining. So it can be written as plus gamma minus 1 by 2 as common, and V2 minus V1 remains, and 1 minus gamma V2 minus V1 is there already. It is equal to 0. Okay. So for these two terms V2 minus V1 is common, right? So A0 square 1 by V1 minus 1 by V2 is nothing but V2 minus V1 by V1 by V2, right? V2 minus V1 is there, and 1 V2 V1 is in the denominator, plus gamma minus 1 by 2 V2 minus V1 is there, and minus gamma V2 minus V1 is there, is equal to 0. So V2 minus V1 is common in all the terms, right? So you can write here V2 minus V1 as common, and what are the terms inside? A0 square by V2 V1 plus gamma minus 1 by 2 minus gamma is equal to 0. Okay. So students, this term maybe this term is A and this term is B. So A into B equal to 0. A into B is equal to 0 means either A is equal to 0 or B is equal to 0. So here V2 minus V1 can't be 0 because V2 will never be equal to V1, because the velocity will definitely change from upstream to downstream across a normal shock. So the supersonic field will get converted into subsonic field. That is the main characteristics of what a normal shock. Definitely there will be a change in an abrupt change in flow parameter. So V2 minus V1 can never be 0. V2 minus V1 can never be 0. That means if A is not equal to 0 means B is equal to 0. So that means B should be equal to 0. Okay. So B is nothing but A0 square by V1 by V2 plus gamma minus 1 by 2 minus gamma is equal to 0. Right. So A0 square. So the other condition was V1 minus V2, V2 minus V1 is equal to 0, right? So V2 minus V1 is equal to 0 gives V2 equal to V1. So this won't be, this is not applicable for, this is not applicable for normal shock wave. Okay. Normal shock wave, this particular solution, there are two solutions, that is either A is equal to 0 or B is equal to 0. So this particular solution is not applicable for a normal shock wave. So only this solution is applicable. So gamma minus 1 by 2 minus gamma is nothing but gamma plus 1 by 2, right? Gamma plus 1 by 2. So you can write it as A0 square by gamma, V1 into V2 actually minus gamma plus 1 by 2, actually minus gamma, so is equal to 0. So this is the solution. So A0 square can be written as 2 into A0 square by gamma plus 1 can be written as V1 into V2. Okay, so I am rearranging where V1 V2 is written as 2 A0 square by gamma plus 1. So this is the solution for our normal shock wave. So students, we have studied a particular equation, as I have told earlier. We have studied in the first module that an adiabatic steady flow energy equation, adiabatic steady flow steady flow energy equation. So do you remember those equations? That equation were like a square by gamma minus 1 plus v square by 2 is equal to v max square by 2 is equal to a0 square by gamma minus 1 is equal to a star square critical acoustic velocity into gamma minus 1 by 2 into gamma plus 1 by 2 gamma minus 1. So such equations were there. So I am taking this particular equation. Okay. So A0 is the equation relating A0 and A star. So A0 square by gamma minus 1 is equal to A star square gamma plus 1 by 2 gamma minus 1, right? So gamma minus 1 and gamma minus 1 cancel. It means A0 square is A0, 2 A0 square by gamma plus 1 is A star square. Okay, A star square. So students, just note that this term is nothing but 2 A0 square by gamma plus 1. So what is 2 A0 square by gamma plus 1? A star square. So I can substitute here V1 V2 as A star square. Okay, A star square. The solution for normal shock wave is V1 into V2. The product of velocity upstream and downstream of normal shock wave is nothing but A star square. So it can be written as V1 by V2 as A star into A star. So V1 by A star by into V2 by A star. So the product of these two terms is nothing but 1. So I have taken A star, both A star to the left hand side. So what is V1 by A star and V2 by A star? So we have already studied a term called M star, right? M star, reference Mach number as V by A star, right? So what is here? It is V1 by A star and V2 by A star. So I can write M1 star into M2 star as product of M1 star and M2 star as 1. So this particular equation, is nothing but Prandtl Meyer equation. So this equation implies that the velocity change across a normal shock must be from supersonic to subsonic or vice versa. So what does it actually mean? So actually this equation, this relation itself can be termed as Prandtl Meyer equation. Okay, Prandtl Meyer equation. So I have rearranged this and I have just transformed that equation to another form, that is M1 star into M2 star is equal to 1. So this equation connects the velocity upstream and downstream of a shock and the critical velocity of sound. Okay, the Prandtl Meyer equation can be written in another form like M1 star into M2 star is equal to 1. This equation gives the idea that the velocity change across a normal shock must be from supersonic to subsonic. Either M1, if M1 star represent a subsonic value, then M2 star should represent a supersonic value, because both their product should be equal to 1. Or if M2 star represent a subsonic value, means M1 star should represent a supersonic value. Okay, because their product should be equal to 1. Okay, but we have already seen that due to restriction imposed by that second law of thermodynamics and that entropy equation and all, change from subsonic to supersonic is not possible. So normal shock must always turn the flow from supersonic to subsonic. So what normal shock? Normal shock is always from supersonic to subsonic. So M1 star into M2 star should be equal to 1 means M1 star should represent supersonic flow. The value of M1 star should be of supersonic, and M2 should be subsonic. M2, and the value of M2 star should be of subsonic. Okay. So that's all for today. So I've concluded the derivation of Prandtl Meyer equation. So very important. Thank you.